same density to immiscible fluid.
How they distribute.
Viscosity doesn't have random.
Did I teach you anything about that? Yes, that's a model for that. That is.
Same density.
Oh, did I press the button? Tell me to can you check if I press the button? Thank you. Same density, immiscible. Don't you expect something like that? Oil, water. Density, is it good? Does it have the red thing?
Yes.
Okay. For oil, density is about 800. Water is 1000 kilogram per cubic meter. That's the flow pattern that you have. So if we have identical, I don't think it's going to be, it will be different. It may be dispersed. It will be something like that. But sometimes I don't know, it may flip up. It should not look, it should look similar to this than gas, liquid case. Okay, double flow, transition G and F, it is already good. Transition B is also good too, but sometimes it is truncated by something else. So for you to fully use it, use the binary version for the unified model for annular flow, okay? Use this graph. That's what I mean. Use that graph. Unify transition J. So double flow, we should consider transition K, right? Transition K is to form the wave, okay? Because the density of the liquid make the wave by itself, and we can check transition C. So for angle less than 5, the theory just show that the theory and experiment show that there's no stratified smooth anymore. When you combine K and C, you can show that less than -5, stratified smooth is just gone, especially for water and air. Okay. All right, this one is a new one. Transition L, -90 to -70. Annular flow falling film. Okay, exists at low gas flow rate. At low gas flow rate, the radial velocity fluctuation can cause a fluid particle to travel from the bottom to reach the top of the pipe wall. See, because of that fluctuation, they develop transition L. Transition L is stratified to annular. Okay, stratified to annular. So this term is a velocity fluctuation in the turbulent flow, right? Single phase turbulent flow. That's a velocity fluctuation. So with the model that the maximum fluctuation is 2 multiplied by square root of v prime squared bar. Then we get fluctuation velocity with this form. Use this formula. This formula is u square v square minus u square equal to 2as. So it's a constant acceleration for particle moving. You still remember this? This from high school, I think. Okay, u square minus v square equal to 2as.
V squared equal to u squared plus 2as.
Yeah, but this time the gravity term go down, so it's kind of minus. After that, we get this formula. S sub r is that distance. Okay. Do some a little bit more trick, then they get transition criteria. That one for transition L. Equation 5.5. We may not. You may get confused about transition L a little bit when we look in the flow pattern map, because it looks like this. See this one? Okay, transition. Okay, let's take a look at this one first. The 5-inch pipe. So, see this transition E. That line, right? Transition B is this line. Okay. So in a big pipe, maybe it looks confusing, but in small pipe, transition B, transition to annular flow, is that line, that long line. Okay. Transition F is still this, and we still have transition G. For the bigger pipe, we have transition E, like bubble flow, but it doesn't really have bubble flow. I don't think I see any bubble flow. So the transition become like this, right? Because it's combined between F, E, and G. This is for falling film model. So if you want to do this, obviously it's falling film model. So with this one, you get the transition L. Okay. We don't use it much. Okay. You will use it more when you do like nuclear reactor. Okay. We don't use this much. If you somehow do the injection and it somehow have gas, maybe you have this kind of transition L. Okay. Transition L is not the same as this is the same. No, it's not the same as the unified transition J. See what I'm saying? So transition J and L, they are not the same. Transition L is based on the fluctuation of the velocity and it reaches the top of the wall. Okay. Unified transition J for Bunny model is based on the balance between force, right? Film falling down, film falling up, and the minimum point. If you still remember, we'll go through it a little bit more. So for downward incline, if you have transition L, you get everything. Then you can generate the map as in the simulator that you have. Will you fully understand this part? Not really, until you do it and compare with the simulator. Then you will really understand it. Right now, you just know the equation, but you haven't plotted, right? So you may, at your own choice, plot it. But you can see in the project, I don't see the place that it can go like a lot downward. In some way, it can. Okay. So next part is about downward vertical flow. In downward vertical flow, we have only annular / dispersed bubble flow. We don't have stratified flow. We have falling film, okay, for annular flow. And for vertical flow, we can use a Bunny et al. Model to do the pressure drop calculation. This model is no entrainment, smooth interface. Okay? And this talk about like the inlet condition is matter, which we talked about that already. So this part, the only thing that you need to do is know how to write this equation and that equation. Okay? Of course, I cannot really test you because it's open book, right? You can just open the book and write it down. But when you see this equation, I want you to understand it. Okay? The first term, minus AL dPdL. So this means this part is P, this part is P plus dP. Okay? So minus AL dPdL is the difference between these two terms. Force balance. Tau L, SL. So when we flow downward, tau L go up, right? You see that one. So in this momentum balance, flowing up has a negative sign. Gravity term flowing down, right? Doesn't have positive sign. Interfacial friction factor, look at tau I. Tau I in the liquid phase, tau I is this part, right? That's the assumption. So tau I is like that, then we have positive. So going down is positive. You have gone through several material already, so you should have no problem to understand that equation. And we have already used it to derive the Bunny model for the unified transition J, right? And we have gone through this geometrical relationship. Have anyone looked at the announcement that I made in the blackboard? Did you take a look on that announcement? What is that announcement about? Yeah, for the project.
Something about the model, what was used.
You remember Title model for slack flow? It is valid for any angle, 0 for 90. But for 90 degrees, how do we do it? For 90 degrees, all of that geometrical relationship has to be like this or something similar to this because it's not separated flow anymore. You see what I'm saying? Not really. In the equation that Arya talked about, Arya, you still remember that equation?
Yeah.
The combined momentum equation for Title bunny. Which page number? Can you help me a little bit? 3.139. Page 102. Remember that equation? In my announcement, I said that equation. This equation still works. Okay, even with the upward 90 degree. But when you use it, instead of ST become 0. Okay, because gas doesn't touch the pipe wall. AF, for AF, film area, right? You don't use you don't use this AF anymore. This one is not valid in that equation. Okay, this AF, AG cannot be from 3.38 because 3.38 is for a stratified model. When it separates like that, even though this equation is still valid, okay, this equation is still valid, but geometric relationship you have to get from the chapter 4 model. Okay, chapter 4 model. You have to get it from here. Okay, AF you change to here. SI you change like this because it's the way that the flow distribute is changed.
This is for 90 degree, right?
If you have slack flow, but you have the film around the pipe instead of the film at the bottom and gas at the top, you have to use this one.
Vertical.
So for upward vertical, for 45 degree, the film on the bottom will be bigger than the film on the top. Any model will be wrong. If you want it to be very accurate, you do both and average it.
Is it because of the film?
If you don't, it's because it is not uniform.
So at 7-8 degrees,
So near horizontal, you can use this relationship, right? Because it's separate. Near vertical, you should use this instead. At the middle, you can average them together, or you can use one of that. Any case, it's wrong. It's not wrong. It's not perfect. It's okay, but it's not perfect. That's my point. Okay, but bunny equation is still good. And I think next lecture we will go through a little bit on that. Let's do next lecture. Let's finish the unified model. For the equilibrium falling-film model, we use transition B. Okay, this one is transition B for calculating falling film, right? So this is nothing new. It's still transition B that we have. Okay, and F and G, E, they are all good. And if you want a better version, okay, you use bunny model. So that's nothing new. Let's talk about the unified model, how people do it. Let's take a look at Gomez. Okay, Gomez et al. Unified flow pattern prediction. They use bunny model. Okay, and unified pressure drop calculation for each flow pattern. So basically, Gomez Step 1, get the flow pattern. Step 2, get the pressure drop. That is valid for that flow pattern. Giant unified model is different. They use one model for everything. Okay, so they start from slug flow. Okay, and when the slug body length is short, that is equivalent to stratified flow or annular flow, depending on how much of the pipe wall is weighted. Okay, if it is LF go to 0, film length go to 0, that is equivalent to this bubble flow. Okay. Alright. Okay. Unified flow pattern prediction for Barney, 1986. They use transition A and they use new transition J that we have already talked about. Transition J, F, and G are modified slightly. Okay. We already talked about how to modify transition J, right? And it is in the exam. Okay. Transition J, unified model for transition J that do all this is in the exam. I found that my slide is already correct. Okay. You still remember this? Require pressure, supply, require shear, require tau I, supply tau I, match them, and it's the solution, right? Okay. So if we do the combined momentum equation, we get that. If we do the minimum point equation after do the derivative, we get that. You remember this? This is in the exam. This is in the exam. You need to know at least the page number, of course. But I can ask you more than that. So if we put point 24 inside combined momentum equation that is in dimensionless form, we get the transition due to film growth, that line. Okay? And you can see that this time you get a curve like this. You don't get a straight line. Right? That is transition J. Next step, we want to see how did Barney modify transition F. Transition F that's valid for any angle can be better. Okay? To make it better, they combine two things together. The first part is bubble accumulation occur due to turbulent force is not high enough to break the bubble. Okay? DCD is about the surface tension, right? So this kind of turbulent force and surface tension, that is the process number one that can make this bubble flow to not stable. So basically, if we don't have enough force to break the droplet, we don't have this bubble flow. Number two is that if we have enough force to break the droplet, but we don't really can make it stay uniformly, so it migrates to the top. When it migrates to the top, so if the bubble is so large, it migrates to the top, then we don't have this bubble flow. We kind of have bubble flow, right? So even though you can form small bubble, but your bubble move to the top, we don't have this bubble flow. So they combine. This one, have you seen it yet? Is this transition D that you have seen earlier in horizontal flow? And this is transition F in vertical. They combine it. Okay, but they combine it. And so what is the equation to calculate? Let me show you instead. So for the first one, they combine buoyancy force and turbulent force, right? This is the same as 3.57, 3.58. Okay, so this is kind of transition D, right? Transition D. So another transition is transition F. So basically, you calculate DCD and DCB, or droplet size from transition D and transition F, and if your maximum droplet size is less than both of that, then you have this bubble flow. It may look a little bit confused, but if you look at the graph, okay, let's look at the graph. That's my graph. Okay, take a look at this. You have this line and that line, right? Basically, you do transition D and transition F, you do both, and you select whatever is higher. So you have this dashed line, right? This solid line. So you select the one that is higher. So this case, you select this one or something. So the only thing that I should ask you is, where is the equation? Okay. So this time we are talking about chapter 5, right? Which part in chapter 5 that talk about the modified transition F? Which part? You see that? Pardon me? Which page number? 206, of course. So you see the equation 4.21, right? That is DCD 4.21 on page 207. Okay, that is DCD. That is the equation for D max. That's equation for D max. That's equation for DCD. And DCB, due to buoyancy, is that one. So the final criteria is whichever is smallest. So to have this bubble flow, D max has to be less than that, and D max has to be less than that. I know that you don't have enough time to practice in the homework, but you should know where is it in the book. Okay, at least you should read the book, not read the book during the exam time. Okay, read the book before the exam time. So you have seen modification from Bunny, right? For transition J and transition F. Transition G stay the same. And you can see that it's kind of look better when we combine everything together. Kind of more accurate. Okay? But if you use transition F, everywhere it's still fine. It's close. It's not that off. But if you want to improve, use combined criteria. Okay? So the rest of this is discussed like, okay, summary. So transition A, equation for transition A is this. Equation for transition F and G is that and that for transition F. For transition J is that thing. So you need to know how do we get that, or where is it in your book at least, so that you can read it more later. So bubble to slug, you still remember this, bubble swarm, but this time we have sine theta. So this is how Gomez et al. Do it. And this is the process that they solve. At the end, you calculate pressure drop. So this is a unified stratified model. Everything that we go through it quick because it's the same. It is the same that we did. So they use different correlation, just that. First, pressure drop calculation. After the flow pattern is known, they use whatever in chapter 3 and 4 to do the calculation.
I have a question.
Okay.
Can you come back? No, to FL.
FL. Friction factor.
Yeah, Uyan.
Okay.
The last one. So the second homework that you got us to calculate the pressure drop of stratified flow. So at the end, the stratified flow in the gas section and liquid section should have been the same to know that you've done it correctly. But if you got the FL from Bouillon, you get something off.
Okay. Did you read the whole process for stratified flow? Once we do the flow pattern determination, we have to revisit that governing equation and solve it numerically to make everything consistent. And it is explained in that page. Did you try to do that? If you do just what I did, it is fine, but it's not going to be consistent. It's not going to be perfect.
You're saying to make everything
If you want,
consistent.
Yes, you have.
You should, for example, use Rapson to get the
You have to
edge.
solve it numerically.
To
Correct.
get the edge.
Redo that, yes. For pattern elimination is one thing. After we know that it's stratified flow, we redo all of that and make everything consistently. So like one equation, one and one. Which pages? 86. That's, this is the calculation step. Okay, step 1, step 2, step 3. So you see, determine, no you can't see, okay. Alright, so basically after we know the equation, we have to redo it. Calculation procedure. See this part? Determine x, get y. Okay, after get x, get y, get h altido. So
what should be solved then?
Yes.
Because H tilt is also known.
get from the chart, right? One must use appropriate individual friction factor. Okay, and then
There is nothing to solve then.
you see this equation? If you substitute that form in,
Yeah, okay.
where's that? Once you get the flow pattern, what I remember is that you have to substitute, if you want it perfect,
Yes.
you have to substitute the governing equation for friction factor inside and solve it one more time. Get
So it's-
one equation, one unknown. So everything will be only a function of
H
h zero, yes. And then you solve for it, and then it will be consistent.
So the repetition that you talk about is from
The problem that you get earlier is because when you get h altido from the chart or from your program, it's not consistent to the closure relationship that you use for tau I.
So okay. So title and money, okay, in the slot flow, they said exactly to do this, that you get H tilt and
Okay.
solve it to make everything consistent.
Consistent.
But here, if you get one H tilt from X and Y, so what are you gonna solve again? So the same H tilt?
Once we know the flow pattern, that is stratified flow,
Yes.
so we get the governing equation, we get the combined momentum equation, not dimensionless. Okay, so we have tau I, tau WL, tau WG, everything in its original form, and we substitute the formula for Fi in it,
I know,
and
but
then solve it simultaneously. One equation, one unknown.
X and Y is
Don't do any x or any y. Use the dimensional form, solve it, then everything will be consistent. Start with the combined momentum equation, not the dimensionless. Okay, then everything will be consistent. Oh, I should repeat that, not do any of this. Okay, we will do this later, next Monday. So the trick is, once you get your chart, get the flow pattern, okay, stop right there, okay, then go back to the combined momentum equation in the dimensional form, and that equation is combined momentum equation is 3.28. You see 3.28? 3.28, page 55. Arya asked the question about how do we make it perfect. Okay, we can make it perfect by start with 3.28. From 3.28, you will. Okay, let's show 3.28. From 3.28, this equation, you will substitute the formula for tau I, whichever you select, into that equation. Okay, tau Wg will be dependent upon V square, right? Tau Wi will be Vg minus Vl absolute value multiplied by from, you can use square. So everything, all these things will be one equation, one unknown with
H tail and
h, yes, then you resolve it again.
yes.
So they suggest use a graph to like
First is
roughly get the answer and refine it later.
yes.
You ready for the exam?
So this is the same way for stratified, right?
Yeah, this especially for stratified wave, yes. Okay. Aya, you want to meet afterward? Or you don't want to? You have more questions? If you have more questions, please meet with me. Okay. See you next Monday. And bring the book. Bring the calculator. Okay. Have a good Thanksgiving.
On Monday?
Bring the book. Calculator.
Just